Welcome to another Royal Astronomical Society's online public talk. Hello, I am Lucinda Offer, Education Outreach and Bicentenary Events Officer for our 200th anniversary of the Royal Astronomical Society. Our organization advocates for astronomy, geophysics, and space science in the UK since 1820. I'm excited to introduce to you today our bicentenary talk guest speaker, Professor Tom Wright, who will speak with us about monitoring our hazardous planet from space using satellite technology. Working with other COMET scientists, which is the UK Natural Environment Research Council Centre for the Observation and Modelling of Earthquakes, Volcanoes, and Tectonics, Professor Wright will show us how satellites are used to monitor tiny ground movements with extraordinary accuracy, and explain how understanding these movements can help us forecast where future earthquakes will occur and when volcanoes might erupt. Tim Wright is Professor of Satellite Geodesy at the University of Leeds and Director of COMET. His work has been at the forefront of developing the use of satellite radar for measuring tectonic and volcanic deformation. He was the first to measure the slow accumulation of tectonic strain around active faults with satellite radar, and he is currently co-leading a major project using the latest satellites to map how all the continents are deforming. In 2018, he co-founded a spin-out company, SatSense Limited, which is monitoring ground movement in the UK at high resolution. Professor Wright has received several awards for his work since 2014 from both the American Geophysical Union and the British Geophysical Association, as well as the Royal Astronomical Society, who also awarded one to COMET in 2018. A quick reminder that there will be a Q&A after the talk, so please get your questions ready. There are places to post your questions for our speaker if you've joined us on Zoom in the Q&A box. And on YouTube, we have a chat box there for you to post your questions. Thank you to Professor Wright for being with us today and to celebrate with us our 200 years of the Royal Astronomical Society. On to you.
Hi, and thank you for the invitation. It's great to be here. This talk was supposed to be live in Leeds, and obviously it's sad that we couldn't do this face to face in person. But it's a great pleasure to see you all virtually, and I hope to hear some of your questions. I want to talk to you about how we can use modern satellites to help monitor our hazardous planet. Before I get going, I really wanted to emphasize that science isn't just a one-man operation. This is one of the work I'm presenting today is the result of a huge amount of effort over many, many years. And I've been really lucky to work with some fabulous collaborators, and I'm really missing them at the moment. Obviously, we see each other on Zoom, but it's not the same as getting around a table and chewing over a nice problem or doing some work properly together. So I put up this slide. I enjoy putting this slide together. It reminded me of all the fabulous people I've worked with over the years. So earthquakes have killed nearly 1 million people since the year 2000. This is a photograph from L'Aquila in Italy, where an earthquake in 2009 killed around 300 people. In Haiti in 2010, nearly maybe as many as 300,000 people were killed in a single earthquake, in a really devastating event. Volcanic activity has resulted in hundreds of thousands of people being evacuated from their homes. Here's an example from Bali on the right. And of course, many of you will remember the unpronounceable volcano from Iceland, which shut down their transatlantic travel in 2010. Closer to home, we also suffer from the hazards of ground movement. So on the left here, we have a sinkhole that opened up underneath Sainsbury's in Ripon in North Yorkshire. And sadly, 3 people recently lost their lives when a train struck a landslip in Scotland. So my messages and take-home messages and themes today really are, firstly, that satellites are playing an increasing role in disaster management and response. I'm going to focus on measuring ground movement. I'm going to talk about how we do that and show that we can do that now with extraordinary precision, and argue that this is a real game changer for monitoring our hazardous planet. And then at the end, I'm going to touch on how we use all this new information and argue that we really need to work across both national and disciplinary boundaries to actually stop natural hazards becoming disasters. So I'm going to start off thinking about the disaster management and response cycle. So often when people think about disaster management, they think about these different phases. So it starts with an event, and there's a response to that, and then there's a recovery period before we go on to mitigation and preparation for the next phase. And satellites can be useful at all of those different stages. They can provide early warning of unrest. They can monitor unrest, particularly in the case of volcanoes. When an event happens, we can use satellites to help understand exactly what happened. Look, for example, at which areas were damaged and which ones weren't. We can try and use the data to understand whether an event, such as a volcanic eruption, is over. Often these aren't just single events like earthquakes. We can think about the ongoing hazard and how we might use the satellite data to inform how we reconstruct the area. And in the long term, we'd like to be able to use satellites for saying something about the long-term hazard from whether it's from volcanoes or earthquakes or other natural hazards. I'm going to start in Nepal in event response on the 25th of April 2015, just at the point that a major earthquake is about to hit. This is CCTV footage. You can see as the earthquake hits, people are rushing out onto the street, and then you can see suddenly they're shaken and really swayed across this little square in Kathmandu as if they're on the deck of a ship in a storm. It's a really remarkable and frightening piece of footage. I'm going to show you the same thing again now, but this time on the top right, I'm going to show you this red dot here, which is the position of a GPS receiver. And that position could be measured to the nearest few millimeters and tracked through time. And this is a video put together by colleagues at UNAVCO. And what we're going to see is how that GPS receiver moved during this earthquake. And the scale here, this is movement to the east is left and right, and to the north and south is up and down. And this bar is a 1 meter scale here. So if we just play that video again, and we just watch that dot and watch the video at the same time, and you can see we get a slow movement to start with as the initial shaking hits Kathmandu, and then we get this sudden dramatic swing of that position of the ground. So the whole ground is moving by a couple of meters and shaking backwards and forwards during the earthquake. Really, in this case, quite a sort of long period, long, slow shaking. As well as that shaking, what you can see is that the final position of this red dot, it's not finally settled down yet, but when it does, it's going to be offset from that original position. So it's more than a meter away. So that represents the real movement of the ground that happened during this earthquake. And we can map that movement not only at the location of individual sensors like GPS receivers on the ground, but with satellites, we can now map that over a wide area. And I'll show you how we do that. But the first time we hear about earthquakes internationally is using a technique called seismology, which is listening to seismic waves that come off the earthquake. And there's a number of organizations globally that provide very rapid solutions telling us where an earthquake happened and how big it was. One of them is the US Geological Survey. And within about 20 minutes of most large earthquakes, they produce an initial estimate of the earthquake. In this case, this was 19 minutes after the earthquake. They tell you where the epicenter was, so that's where the earthquake started, and give you an estimate of the magnitude. In this case, the initial estimate was 7.5. And as well as that, they use that information to provide an estimate of how much the ground shook during the event. And that's on this scale at the bottom, where light blue or white is very little shaking, and we go up to red, which is extreme violent or extreme shaking, where we might expect heavy or very heavy damage. And you can see the initial estimates have these kind of yellowy orange colors, so prediction of strong to very strong shaking with light to moderate damage. Now, after about 52 minutes, the first update on this map was produced, and you can see that the intensity of those colors has already increased. So we've increased the magnitude to 7.9, and we're going up to these darker orange colors. As time evolved during that first day of the earthquake, those solutions gradually changed. The biggest one was after about 4 hours, when the seismology went from being a point source, which is the initial description of the earthquake, to an extended source. Now, earthquakes don't just happen in one location. They happen when a whole fault slips. And in this case, a fault that was more like 150 kilometers long slipped during that event. And you get shaking all the way along that event. And often, as you can see in this case, it happens in one side of the epicenter. So you can see in this, if we compare the point source solution with the extended source solution, for Kathmandu, you can already see this much stronger, intense shaking, these red colors around Kathmandu. So this was saying that Kathmandu was likely to be damaged. And after 15 hours, this was the final solution from seismology alone. Now, one of the issues with seismology is that because we're using globally measured data, it's actually quite blurry. Often the locations aren't perfect of where we're expecting strong shaking. And this is where the satellite data can come in really handy. So this is an image, and I'll talk about how we produce this. This is an interferogram from a technique called INSAR, and this shows the ground movement during the earthquake. So here's the epicenter over here, and here's Kathmandu here, and these colored interference fringes showed how the ground moved. So let's talk you through what we're seeing here and how this method works. Here's a cartoon to try and explain this method called INSAR, and a lot of the results I'm going to show in this talk are from this technique called INSAR. So this is a diagram that's not to scale. Here's a house. This satellite is flying at around 500 or 600 kilometers and it's sending down radar waves. These have a wavelength of about 6 centimeters. So there's actually 30 million of these waves between the satellite and the ground. Now, the satellite, every time it flies over, it sends these waves down and measures the reflections. If it comes back at a later time and the ground has moved, for example, in an earthquake, then the distance between the satellite and the ground has changed. And it's that, although we don't know the precise distance in terms of the total number of wavelengths, we can measure this very small change extremely precisely. And that's the interferogram part of this process. And that's what we see in these colored maps. What we see is these small changes in distance between the satellite and the ground. And every time we go through a cycle of these colors, the total distance between the satellite and the ground has changed by 1 whole wavelength. So the ground, in this case, has moved closer to the satellite by half a wavelength because the round trip is there and back. So half a wavelength is about 3 centimeters. So you can count these interference fringes, and there are a lot of them. There's 1, 2, 3, 4, 5. There's something like 30 or 40 interference fringes up to the maximum here. And we can also get the computer to do the counting and give us a continuous scale here in red. So the stronger the red colors, the more ground movement there has been towards the satellite. And there's been more than a meter of motion towards the satellite just north of Kathmandu. You can also see these blue colors further north, and they're showing subsidence, movement away from the satellite, and again up to a meter or more of movement in the closer to the further away from the satellite due to this subsidence. So what's going on in Nepal? What's going on in an earthquake like the one we had? Well, we need to step back a little bit and look at the collision of India with the Eurasian plate. So here's India here, and it's moving to the north and colliding with Eurasia at a speed of around 40 millimeters per year. And that's creating the Himalayas, but also this massive collision zone ahead of the Himalayas, the Tibetan Plateau, and all these mountains. All these black lines are individual faults. The motion that's taken up by squashing the Himalayas, if you like, movement on this fault, this arcuate fault at the front here, there's about 15 millimeters, 1.5 centimeters of motion every year along that fault. But it's stuck. And I'll show you in a cartoon. The earthquake happened here. And if we look at a cross section of that in this nice cartoon that's produced by colleagues at Caltech, you can see India's moving forwards. That shallow part of the interface between the Indian plate underneath and Eurasia on the top, That shallow part is locked for most of the time. So that's stuck together, and as India moves, it bends that upper plate, and then gradually suddenly during the earthquake, we release all of that stress that's accumulated over many tens or hundreds of years. We can just go through that a little bit more slowly in these cartoons on the left. So between earthquakes, this upper part is locked. We're pushing on India, so it's stuck. Friction is holding those two sides of the fault together. Below, in the deeper part, it's freely slipping because the rocks are hotter and weaker down there. So it's stuck by friction, the stresses are building up, and during that time period, this part subsides, it's kind of bending down, it's being dragged down by this stuck part of the fault, and this part here uplifts. And during the earthquake, the opposite happens. So this locked part of the fault breaks. We end up with slip here in the earthquake, many meters of slip often, and that causes uplift above where the slip happens and subsidence in the high mountains to the north. And that's what we see when we look at the map view of the data from the satellite. So we've got this area of uplift and this area of subsidence, as well as motion to the south that we saw in that GPS receiver. And we can take that data and actually use a geophysical model to try and understand what happened on the fault interface itself. So here's another 3D view. Here's India diving down beneath the Tibetan Plateau. And this is the fault. And these colors here show the amount of slip that happened on this part of the fault. And you can see there's up to about 6 meters of slip in this case. Mostly happening on the lower half of the fault down to about 15 kilometers. And one of the interesting and worrying things actually about this earthquake is not which bits slipped, but which bits didn't slip. And this shallow part, which we also think is locked between earthquakes, didn't slip. So we still think the stresses here on the shallow part of the thrust have not been dissipated in the earthquake. And so at some point, we're expecting a large earthquake, another large earthquake near Kathmandu. Kathmandu's on about the boundary between this slipping patch and this locked patch. And in the context of this talk, in terms of satellites, what we can do now is respond to these events, really find out what happened in great detail within a few days of every earthquake. And that time window is getting shorter and shorter as our analysis tools and our speed of getting the satellite data gets shorter and shorter. And we can take that information, communicate it to local people and to decision makers, to colleagues, as scientists working in Nepal as well. So what difference does it make to the shake map? If we'd had that information earlier, could we have said something better about which parts of the area were affected by strong shaking and which ones weren't? Well, the USGS updated their shake map using the information from satellites, and this is what they get. They didn't do this until about 10 days after the earthquake, but it demonstrates the impact of the satellite data. So we go from without the satellite data with this kind of rather broad pattern of yellows and oranges around Kathmandu to a much more concentrated area of shaking with these redder colors in the mountains north of Kathmandu. Sadly, around 10,000 people died in this earthquake, and many of those were in the mountains to the north of Kathmandu, where this incredibly intense shaking caused some devastating landslides. And so really, I just wanted to emphasize that incorporating this satellite deformation data changes the prediction of ground shaking. And we hope that within the next few years, as we get better and better satellite data, incorporating this kind of information will become more and more routine and will provide better information rapidly to decision makers. As well as the information on predicted shaking that we can get from doing the modeling of these data, we can also directly use the satellite data to look at areas of damage by comparing images before and after the earthquake. And this is an example of that work done by the ARIA group at NASA JPL. And these red colors show areas of predicted damage based on changes in the radar image. And you can see that they correlate quite nicely, unfortunately, with these areas of very strong damage. The Sentinel-1 satellite is a satellite I'm going to be talking about mostly in this talk, and it really has changed the way we do this. It's an operational radar satellite, the first one, first of these radar satellites that's truly operational. It works like all radar satellites. It works in all weathers. It's sending radar waves out day or night, and those radar waves can see through clouds. So we can. It's a system that works whatever the weather. There are systematic acquisitions from Sentinel-1 over the whole planet, at least twice every 12 days, often twice or more every 6 days. So we're getting a lot of data. It's designed for this INSAR technique, which effectively means it has a very boring acquisition strategy. So it's always in the same mode in every single acquisition. And so it means we can make these comparisons very easily. And it's funded for a long period of time, 20 years or more. The first of the satellites was launched in 2014 and the follow-up in 2016, and there are backups now ready for launch in the next few years. And also importantly, the data are completely free and open. You can register with the European Space Agency and download these data for free and analyze them for free. So we can build systems that rely on this data and use large volumes of the data. And we're trying to use it in COMET to look at all of the global volcanoes and all of the global fault zones. So we're going on a bit of a tour around the world here. I'm going to talk about one other earthquake, and that's an earthquake that happened in New Zealand in 2016, a really incredible earthquake. You'll see in this photograph one of the most incredible pieces of earthquake fault damage. This fault went right underneath this farmhouse, and it ripped the house from the foundations, from its foundations. You can see the foundations here, and here's the house. Amazingly, there was someone in this house, and they were able to walk out, which is testament to the way this house was built. But that fault went through there. It offset by about 10 meters, so a huge amount of displacement. This earthquake sadly killed 2 people, but for an earthquake of this size, actually that's a very small number. And a lot of the media attention was actually about these cows who got stranded on this landslide here as a result of the earthquake, and they had to be rescued at enormous expense by helicopter. Now, this earthquake's interesting for a huge number of reasons, but one of them is that the initial seismology got the solution completely wrong for this earthquake. So this was the initial shake map, again from the US Geological Survey, and this is their fault that they thought had slipped during the earthquake, which is actually a deep fault on that dives underneath the north part of the South Island of New Zealand, and they were expecting the slip to have happened on that from the initial seismograms. When we got the INSAR data back within a couple of days of the earthquake again, what we saw was really astounding. We had this incredibly complex deformation pattern. All of these pink lines are places where we could see actual fault breaks in the shallow crust, with huge amounts of movement, again up to 5 or 6 meters of movement or more here around these faults, a very complex pattern. And when that information was used in the USGS to update the USGS shake map, what you can see is a completely different earthquake. So we've got all of these fault segments that were involved. If we compare it to the seismology only, we've got a very different solution. Okay, well, so what? Well, the first thing is, of course, if we could do this quickly and get this information out, this would provide a much more reliable and robust means of saying which areas are likely to have been damaged in the earthquake. We're getting much more strong shaking because of the shallow crustal faults. Secondly, we were able to work very closely with actually a former UK PhD student from the COMET group, Ian Hamling, who is now employed at GNS Science in New Zealand, who are the local monitoring agency. They were able to take our data, give that information to the field teams, both in their office in Wellington, but also to field teams around the country. They were able to then in turn use that data to go out, locate the fault breaks on the ground, really capture incredibly valuable data. And in New Zealand, it rains a lot, and a lot of this washes away after a few days. And at the same time, we were able to use the data to build a 3D computer model, again, of what happened during the earthquake, which faults slipped. And this in turn enabled us to really investigate in detail what was unusual about this earthquake. And it turns out that the Kaikoura earthquake actually ended up breaking a whole bunch of rules in quotes, of that earthquakes should normally obey. It broke a complex network of faults rather than a single fault. Several of those were unmapped and these faults were not expected to fail together. And there were big jumps up and often 15 kilometers between these different fault segments. And also at the same time, we had the deep, we do think there was some slip on that deeper fault underneath the northern part of the South Island. And that deeper slip seems to have happened at the same time as the crustal faults. And so this information is now being used, and this new understanding of earthquakes is being used to change seismic hazard models around the world, including in Los Angeles, where potentially some of these complex multi-fault ruptures might happen. So no prizes for guessing the next location, but we're going to go to the Galapagos Islands, which is obviously famous for its incredible wildlife, but is also a volcanic set of volcanic islands. Here's a view from Google Earth of some of those volcanoes. This one here is called Cerro Azul, and this is a place that we were asked to look at in response to a request from the monitoring agency in Ecuador. And they'd observed some earthquakes that happened around the summit of this volcano. And so we had a look at what the INSAR data was showing in this case, and this is work done by Marco Bagnardi. And what we were able to show is that there was subsidence around the summit and uplift off to the southeast of the summit. And normally, if we think of a volcano that's about to erupt, it normally uplifts in the location where it erupts as the magma comes closer to the surface. So the fact that there was this subsidence in one location and uplift in another location actually indicated that the magma was moving sideways in the subsurface. And this was part of the evidence that local scientists used in conjunction with decision makers to lower the alert level. This didn't erupt on this occasion. A volcano that did eventually erupt was one in Bali in 2017, Mount Agung, but it was a slow burner. So the initial earthquakes happened in August in 2017. Those earthquakes really started kicking off in September, October, but actually they had died down by the time it eventually erupted in November. But all through that time period, the volcano was gradually inflating. And COMET scientists, particularly Fabian Albino at Bristol and Juliet Biggs, were able to monitor this slow deformation and provide that, again, information, working with local partners that helped understand what was going on here. And that leads us on nicely, really, to the next theme, which is about monitoring our hazardous planet. So rather than just responding when a disaster happens or a natural hazard happens, instead, what we'd like to do is actually monitor the behaviour of all the volcanoes and all of the fault zones and other hazards, and say something that helps us forecast potential hazardous activity before it happens. And deformation at volcanoes is really useful. It's diagnostic of impending eruption or unrest. This photograph, by the way, is of Mount St. Helens in the US. So some nice work by Juliet Biggs and Susie Edmeyer, published in 2014, looked at all of the examples in the literature of volcanoes that had deformed. And of the volcanoes where they could measure deformation, about half of those had eruptions. Whereas if they saw a volcano hadn't had any deformation, almost all of them didn't erupt. A few of them did. And this may just be because back then we didn't have Sentinel with regular data acquisitions. And we're now building within COMET a volcanic and magmatic deformation portal where you can go to any volcano in the world and look at the active deformation in that volcano. This is an example from Sangay volcano in Ecuador, where you can look and interact with this data and see that over the last 3 years or so, we've had about 30 centimeters of uplift since January 2017. So a really large amount of uplift. I picked this volcano because 5 days ago this happened. So that uplift gradually has led to this major eruption, which has caused a large amount of ash to be deposited in the local area. Let me see if I can get a picture of the ash. Sorry. So it's really covered a very large area in thick ash. So this is incredibly hazardous. But we work very closely with the institute in Quito that is responsible for monitoring this, and they were looking at the INSAR data and knew about the inflation at Sangay. And so that does give some long-term preparation in this case. Now, volcanoes to a certain extent are a more straightforward problem than earthquake faults. Firstly, we know where most of the volcanoes are. They're also point sources, and they have this, sometimes have this precursory deformation, and certainly eruptions are associated with deformation. Earthquake faults can be more challenging. So first of all, we don't know where all the earthquake faults are. Secondly, earthquakes seem to happen often without any precursory, short-term precursory signals, whether that's from deformation or from other factors. Now, some faults we do know where they are. Here's Turkey. There's the Eurasian plate here, and Turkey's in this kind of collision zone. We've got Arabia moving to the north, Anatolia moving to the west, and you can see just in this Google Earth image, you can already see this big scar running through the landscape. Here, that's the North Anatolian Fault, which is a fault on a similar length scale to the San Andreas Fault in California. If I just draw that in, you can see it very clearly there. This major fault, that's slipping at around 25 millimeters every year. Actually, of course, it doesn't slip by 25 millimeters per year. Much like those faults in Nepal, it's stuck most of the time by friction. And then periodically, maybe every 200 years or so, it slips by 5 meters in big earthquakes. And that happened during the 20th century. This is a graph here showing those different earthquakes that happened in a sequence along the North Anatolian Fault, starting in the east with this very large earthquake, magnitude 7.9 in 1939, and then gradually progressing along the fault. You see in around 4 meters in most of these earthquakes, most recently in 2 earthquakes in 1999. And we're of course worried there's a seismic gap south of Istanbul where we might expect a future earthquake. So what's happening around these earthquake faults? Let's just look at a cartoon again like we did for Nepal. Here's a piece of the ground around that fault along the North Anatolian Fault. If we then just look at what happens to that during, as we put time on the clock, so maybe after about 200 years, we've bent this piece of real estate, we've built up elastic stresses. It's like bending a giant piece of rubber or putting tension in a spring. We're gradually building that tension, and eventually what happens is that builds to an extent that it overcomes the friction on the fault and slips. And when it slips, that rebounds back. This line here that was put down before the earthquake has this characteristic shape to it. But what we're really interested here is this interseismic phase, this bending, because that bending, or if we can measure that bending, the interseismic bending or the strain, we should be able to determine how often earthquakes occur in a given location. So can we do that? Well, and does it work? Is there a relationship between that bending, between that strain, and between earthquakes? Well, people have done this with GPS data, so these are sparse data on the ground, and in both eastern Turkey and California, here you can map the strain with GPS, map that bending, and you can see these red colors are the areas of high strain, and the corresponding figures on the right-hand side show the rates of earthquakes, and you can see there's a good correlation between the earthquakes and the strain, and we think that's a causative correlation. So the bending is causing those earthquakes. So strain does correlate with earthquakes, but actually we need to be able to measure it incredibly precisely. So we're talking about, to make a difference here, to get better seismic hazard estimates using strain data, we need to measure length changes of 1 part in 100 million. So we're talking about movements of 1 millimeter per year, 1 millimeter per year over lengths of 100 kilometers. So these are really, really small changes. But we can achieve that using data if we use hundreds and hundreds of radar images, and Sentinel-1 is really providing the ideal tool for that. So here's an example of how we've done that recently in Turkey. So here is one of our radar frames covering Turkey, and we can actually do that. We have lots of frames covering the whole country. We can stitch all of those together, and what we can see here in this cartoon is we've got this blue color of most of Turkey, and that's because the radar is looking sideways. On the first, and when the ground moves horizontally to the west, the satellite's looking east when it's going from, let me start this again. So on an ascending satellite path, the satellite's flying from south to north, and it's looking to the east. And if we have westward motion, that means the distance between the satellite and the ground has got shorter by this blue vector here. So blue colors mean on an ascending path are consistent with westward motion. If we look as the satellite goes from north to south, that's a descending path, it's now looking to the west, and that westward motion is away from the satellite, and so we get this increase in distance between pass 1 and pass 2, so we get these red colors. You can see that in both cases the major change in color is across the North Anatolian Fault. You can then use that data to solve for the east-west and the vertical velocity field. If we look at the vertical to start with, we've got some quite large motions here. They're quite scattered around Turkey. They're not really caused by the tectonics. They're mostly caused by things like water extraction around the Konya Basin here, associated with agriculture or some areas of mining. The horizontal field, on the other hand, shows beautifully the tectonic signals. You've got this very sharp change in color across the North Anatolian Fault, and also here across the East Anatolian Fault. And we can then use that data to calculate the amount of bending that's happening in any one location. And these bright colors here in this figure show the amount of bending that's happening. And you can see this really strong bending across the North Anatolian Fault, some strong bending across the East Anatolian Fault. Also in Western Turkey, we've got some bending associated with some extensional faults there. But actually, we don't get down to the white colors anywhere. There's some strain all through Turkey, which means although the hazard is highest on the big faults, there's still some earthquake hazard away from that. And if you can compare the map of strain to a map of seismic hazard produced essentially from looking at the geological faults and histories of previous earthquakes, you can see there's a good correspondence. Now in Turkey, they have a fantastic history of looking at historical seismic data, mapping faults, which means they can produce fairly reliable seismic hazard maps. In other countries, there's less good data available, and so we want to be able to use this remote sensing technique to map strain across a very large area in order to help improve seismic hazard models. And in particular, we're focusing on the Alpine Himalayan belt, which is a region that stretches from Italy all the way through to China. And this is the region where when a big earthquake happens, lots and lots of people are affected. And the size of these circles, sadly, is the number of people who died in each of these earthquakes. And 3/4 of the earthquakes that killed more than 10,000 people since 1900 have occurred in this Alpine Himalayan belt. So we're in the process of processing all of that Sentinel-1 data across that entire Alpine Himalayan belt. And this is a huge team effort from a large number of us, trying to actually produce then improved deformation maps and then feed those into improved estimates of seismic hazard. And all of this is done in an open and freely available way. So you can go on the COMET website and download the process data and use them as you wish. At the same time, more closer to home, I've been involved in setting up a spin-out called SatSense at the University of Leeds, and there we're using INSAR data from Sentinel-1, processing it at a very high resolution to monitor hazardous ground movement in the UK, and we're keeping that data up to date. And so I want to show you an example from Ripon in North Yorkshire, which you'll remember from one of those news articles early on about the hole that opened up underneath Sainsbury's. So if we zoom in on Ripon, you'll start to see this red blob here, and in this colour scheme, red is subsidence. And if you look here, this is Sainsbury's in Ripon. There's this nice red signal, and we can click on individual points and see their time histories during this 5-year period of Sentinel. And you can see just when we had the sinkhole opening up in August 2018, we've got this bending beforehand and the strong signal as that sinkhole opens up. So this data we think has got a value in both in terms of seeing what has happened, but also potentially in predicting where these things might open in the future. If we look at London, you can see the blobbiness around here. Often these blobs are associated with individual building projects, but there's also this line that runs through the data, and that's showing motion subsidence associated with the Crossrail tunnelling, and everywhere there's a larger red blob is one of the train stations associated with that. So we're now starting to routinely use satellite data for actually monitoring these very small ground motions, and I think this is changing the way we monitor and live with hazards on our planet. And so the final few minutes I want to talk about stopping natural hazards becoming disasters, and I want to argue that we need transnational and transdisciplinary collaborations and partnerships. To set the scene, I want to go back to Haiti, where, as I mentioned, somewhere between 100 and 300,000 lives were lost. And one of the tragedies of the Haiti earthquake is actually we don't know how many people really died in that event. And that tragedy is compounded by the fact that geologists and geophysicists knew that there was a hazard here. So this is a quote from a paper published a couple of years before the earthquake. So the Enriquillo Fault in Haiti, which is the fault that was responsible for this earthquake, is currently capable of a magnitude 7.2 earthquake if the entire elastic strain accumulated since the last major earthquake was released in a single event today. So people knew about this event. And I'm a big fan of the No Natural Disasters campaign. And their motto really is that while some hazards are natural and unavoidable, the resulting disasters are almost always have been made by human actions and decisions. And often we use this phrase when we're thinking about earthquakes in particular, that earthquakes don't kill people, buildings do. It's a phrase that was attributed to the late Nick Ambrases. Now that's true, but who allowed the buildings to be built? And why was resilience to seismic shaking not a priority? And clearly these are complex questions and are beyond mere measuring scientists like myself to answer. And it's not something we can easily address by ourselves. And so the focus now and over the last 5 to 10 years has been about building international collaborations between physical scientists, social scientists, practitioners, working with decision makers and policy makers to try and actually use the scientific knowledge, understand the barriers to that uptake, and really try and improve resilience and prevent natural hazards becoming future disasters. And satellites are playing an important part in that. And again, I want to emphasize the transnational collaborations here, and in particular, the incredible fleet of European satellites that are developed by ESA, and most recently the Copernicus satellites that are operated by ESA but funded by the European Commission's Copernicus program. It really is the best fleet of Earth observation satellites that exists and has ever existed, and they can only really work because a transnational partnership is funding and supporting those. So we're really hoping that whatever happens with Brexit, that we will continue to contribute and be part of the Copernicus program. It's really important for all sorts of things, not only for hazard science, but also for monitoring climate change and signals associated with that. So that's where I want to end it, and thank you very much. And I'm happy to take some questions.
That was excellent, Professor Tim Wright. Thank you so much for joining us. Yes, we definitely have time for questions. We have about approximately 10 minutes if you go a little bit past our end time at 7 o'clock. We have some people joining us on YouTube, so there's a chat box that you can post your questions to there. And we also have a Q&A chat box in Zoom if you're joining us. Thank you for those who are with us this evening. We already have a question in the queue. And your very informative presentation today about talking about our dynamic world. And of course, we have a UK audience for the most part. And this question is about home, something that you and I discussed before your earlier talk. We have a question here from John Murrell, who asks, do you see any ground changes from small earthquakes, such as the recent swarm peaking at 3.5 magnitude in Leighton Buzzard? That was in Bedfordshire, I believe.
Yes, you're not testing me on the county that Leighton Buzzard is, but there were definitely some small earthquakes in Leighton Buzzard, and they're actually smaller than we can usually detect with INSAR. So to see the signals from earthquakes, we need maybe a centimetre or two of ground motion, and what you get from an earthquake like the ones in Leighton Buzzards might be more like a few millimetres, and it also depends on the depth. So we haven't yet seen those. It might be that with monitoring the long-term signals and looking for very small changes that we can do that once we have lots of data, but they're a little bit small for the kinds of signals that we see. So the smallest earthquakes that we can see tend to be magnitude 5 earthquakes, and we can only see those if they're very shallow usually. But it's something we should have a careful look at, and as the data come in over the next few weeks and months, we might be able to tease out a signal, and we'll certainly have a look.
Okay, great. Yeah, it's as someone who's originally from the Bay Area, San Francisco Bay Area, California, and who's grown up since I was born with earthquakes on a pretty constant, regular basis, and volcanoes. You showed Mount St. Helens in your presentation. It's very normal for me to experience these earthquakes and things, and not so much for people in the UK. So it's a really great kind of experience to have here. I know there is geologic activity, but not as prevalent as we have on the San Andreas Fault in California. You also mentioned that it's really impressive what you can do with satellite data, especially to kind of measure what might be happening. But you want to make a distinction about prediction and what that is, and that's not really a word that you use. Could you talk a little bit about that?
Yeah, in fact, we sometimes say the P word because we just don't like talking about prediction, particularly for earthquakes. I think for volcanoes, they can be predictable in terms of we can see signals, whether that's from deformation or from small earthquakes that happen prior to an eruption. But for earthquakes, there's not really been any reliable precursory signals. So some earthquakes have small earthquakes before them that once we've had the later earthquakes, we know that they were foreshocks, but we also have lots of small earthquakes that don't lead onto bigger earthquakes. In the last few years, however, there have been a few tantalizing signals of deformation transients that have been detected, so little bits of deformation that are happening over weeks and months, sometimes years, before some of the larger earthquakes. So I think there's some tantalizing signals there that are worth investigating more. But it may be also one of the other things we've discovered in the last few years is that we can have slow earthquakes, which is places where faults start to slip silently but faster than normal, slower than regular earthquakes, but but faster than they normally slip. And it may just be that sometimes slow earthquakes can trigger major earthquakes. So it's a long-winded way of saying, for earthquake science, we're much more comfortable thinking about forecasting. So can we work out the probability of an earthquake in the long term? And that's, in a sense, probably more useful, because that then provides you information on how you should build your buildings properly to be resilient to those earthquakes. Because I think it's highly unlikely we'll ever get to a situation where we have a reliable earthquake forecast such that we could use it to properly evacuate buildings.
Okay, great. Some more questions that kind of prompted from that discussion. But we have one here from Chi, who says, thank you for your amazing talk. And they ask, from the data, do we know when the red blobs along the crossrail will become hazardous?
Yeah, so they're very small amounts of motion, really. So just maybe a centimetre or so in total, and they've now settled down. So while they were tunneling, there was a lot of active monitoring, both using satellites but also using instruments on the ground to really, obviously you're going tunneling under some really expensive real estate that you don't want to damage. And so there was a lot of monitoring, a lot of remedial work to try and prevent any damage from that ground motion. So it's relatively small amounts of motion. And I think one of the things we're still working on and doing a lot of, SatSense are doing a lot of work on, is trying to understand how much ground motion you need to cause damage. And that's something we're still trying to understand. And I think the answer is it depends on what on your buildings and your situation. Now, if your whole town is moving up and down, then that probably doesn't matter. But if you're bending on a very local scale, that can cause you some significant damage. So there's lots of ground motion, particularly in the old coal fields in the UK. That's one of the most hazardous areas. Yeah, so there's no simple answer, I think, to the exact threshold that gives you damage.
Okay, so a question from Sheila Peacock. Thank you, Sheila, for your question. She says, great talk, Tim. And she asked, can you predict individual landslides? So we've talked about volcanoes and earthquakes. What about landslides?
Yeah, thanks, Sheila. Yes, so we can see landslides. And again, it's the P word. So it depends on the speed of the landslide. So if the landslide is triggered by a sudden rainstorm and then just suddenly collapses, and that's probably unfortunately what happened in Stonehaven, it becomes very hard to predict those. On the other hand, some landslides are slower moving, and they really continually move over many years, and we can see some really nice signals from landslides in various parts of the country in the UK data set. And so those steadily moving landslides are quite easy to track. And then to make the link to prediction, I think what you need is then some modeling. You need to understand what it is, what are the thresholds for your particular landslide, how does the movement relate to rainfall, for example, and actually build a model that you can use the deformation data as part of the story. You might see acceleration before a landslide failure, but you really need to look in detail at each individual landslide and think about how they work, I think. But you definitely can see landslide movements.
Okay, excellent. I'm going to go to YouTube for a question and then come back to Zoom. So the satellite, the deformation data that you're looking at things that happen on the surface of Earth. We have someone who's listening in on YouTube ask about hurricanes. So the satellite data you're getting at, are you looking at weather or climate? Are you just looking at the surface and the dynamics of Earth?
Yeah.
Okay,
so we are, yeah. So we're looking just at the surface. We're seeing through the atmosphere, and actually one of our biggest sources of noise in the data is what's happening in the atmosphere, because we think of light as the speed of light as being constant, but actually it's only constant if you're in a vacuum. And if you've got changes in the weather system, the atmosphere actually slows down the radar waves by as much as equivalent to as much as a couple of meters of extra ground movement, and that is highly dependent on pressure and temperature and humidity. And if they change, then you can get some very large signals. So I think there is potential in the long run of using what's noise for me as a geophysicist interested in the land surface, actually to make high resolution maps of the weather systems using the delays and the noise signal in the radar. And there's various groups around the world looking at doing exactly that with the radar data. But for what we want to do at the moment, it's a noise source rather than a signal.
Yeah, the reason I went into that was the question was about hurricanes and activity in the Atlantic recently, which is a valid question. And they're asking about increase of storms, but that might be outside of this talk.
Yeah, I think it's probably outside the scope of the talk.
Yeah, exactly. So their second questions, it does involve earthquakes. And they're asking if there's a connection between fracking or from undiscovered faults, does that have an increased effect on having earthquakes?
Yes. So essentially, when you frack, you are causing earthquakes. Now, most of those earthquakes are small, but actually the reason fracking has stopped in the UK is that there were some bigger earthquakes than were deemed acceptable in terms of local shaking. So anything you do to the subsurface will cause earthquakes. Most of those will be small. You need to have a system capable of big earthquakes in order to have a big earthquake, but we also are constantly surprised by what happens in the subsurface. So I think personally, the reason we shouldn't frack isn't because of the earthquakes in the UK, at least. I think the reason we shouldn't frack is we should keep fossil fuels in the ground. But in other parts of the world, there can be bigger earthquakes. Often the bigger earthquakes they've had in the US have been associated with injecting wastewater back into the subsurface, and that can cause even bigger earthquakes.
Okay, really good information. We have a couple of questions from Martin Steele. So their first question is, well, first they want to say thank you so much for your talk, Tim. And does INSAR provide any resolution on slow slip events?
Thank you for the question. Yes, there's been a few studies of slow slip events. We had a student, David Beckart, who was one of the, who's now at NASA JPL, and he, as part of his PhD, he was able to see signals associated with a slow slip event in Mexico on the subduction zone interface. And also other people have seen some slow slip events, both on the San Andreas Fault, but also on the North Anatolian Fault in Turkey. So yes, you can see them, and the advantage again is because you don't need the instruments on the ground, you've got the potential for monitoring these over a much larger area. So yes, I think it's potentially a powerful tool. The signals are quite small, so we get to the issue of signal to noise issues, but they can be done. And there's some, I think some, in fact, well, I have a PhD that's about to be advertised, hopefully looking at exactly this topic. So if you're interested in it, then come and study it.
Excellent opportunity there to do a PhD. Excellent. So Martin's second question asked, does INSAR yield any information about oceanic earthquakes too?
You can only measure the motion of the land surface. So the water, obviously, any land that moves underneath the water, although you'll get some water surface movements in tsunamis, etc., there's no permanent movement of the water surface. Plus, the water surface is constantly changing, and so the radar doesn't work there. But oceanic earthquakes, big subduction zones, often cause deformation on land as well. And so you can measure that part of the signal or anything on an island, but you can't measure anything from earthquakes that are a long way away from land. There's potential for using sonar and a similar technique, but it's pretty challenging. It's been shown to be theoretically possible, but one of the issues is that the speed of sound in water changes a lot as a function of temperature and salinity, and so it's you get a large error sources if you try and do it offshore.
Okay, so we have a question from Derek and Jenny. They have a son who lives in Yokohama, Japan, an area where there are large faults, and they had a large one in Kobe, maybe a decade or so back. Is any work being done to forecast the likelihood of earthquakes in the future?
Well, a huge amount, and a huge amount of fantastic earthquake scientists in Japan. So Japan is one of the places where they really, after the Kobe earthquake, which was incredibly, 25 years ago in 1995. In fact, there was an anniversary meeting just earlier this year for that event, they after that earthquake, they really invested very heavily in earthquake science and modern earthquake science. Lots of instruments. You can barely walk in Japan without bumping into a GPS receiver or a seismometer that's aimed for monitoring things. So there is some fantastic earthquake science and hazard information based on satellite data, but also ground-based data in Japan. And if you go to the various Japanese monitoring agencies, the JMA is the main one. You can find lots of specific local information about faults.
Well, I was really off there by a decade and a half, 25 years ago. That is fun.
Time goes too quickly. Yeah,
it does. We have just a few more questions. If you're okay to maybe 3 more minutes to take a couple more.
Absolutely, no problem.
Thank you for that. Claire Granger asks YouTube, she says, thanks, Tim, great talk. Are you able to evaluate historic deformation from field records and pre-satellite data in a meaningful way alongside this new data? And do you use artificial intelligence in the interpretation?
Okay, that's 2 great questions. Thanks, Claire. Firstly, yes, it's really, what we see now is the current day deformation is only a snapshot. So one of the big endeavours, and particularly COMET colleagues in both Oxford and Cambridge are really strong at going out there, looking at historical information on faults and actually going in, digging trenches across faults, doing lots of investigation to try and date when previous earthquakes happened. And that's really important because actually when we see the current day strain, we're only seeing part of the story really. First of all, we don't know really whether that strain rate is constant through time. Secondly, there's lots of ways that we can release that strain in different sorts of earthquakes. So actually linking what's happening now with information from historical earthquakes on the ground is really important. And one of the main goals of COMET at the moment is to try and bring all that information together, look across those different timescales, and really understand everything together in terms of the hazard. The second question was about artificial intelligence and machine learning, and that's something we're really working on as well. Again, within COMET, particularly my colleagues Juliet Biggs in Bristol and Susie Ebmeyer and Andy Hooper in Leeds have been particularly focusing on using it for volcanoes and developing tools that can actually look at this vast amount of data. Every time the satellite goes over a volcano, they can analyze, the machine learning algorithms can be trained on known deformation sources to try and produce flags of either when a volcano is behaving in a different way to how it normally behaves, or when these algorithms see a deformation type signal on the volcano. And we're already starting to roll out some of those algorithms live. So we'll have real-time information that's using machine learning on these kinds of data sets. And I think it's a really exciting area for future research.
Absolutely. I'm actually really impressed on the efforts in the UK to talk about data science to even primary students, obviously secondary students going into university. But we start them early here talking about data science because we're getting so much data back from satellites that actually needs analyzing, and that it may even be just, and artificial intelligence can definitely help us with that.
Yeah,
so,
and it's also becoming incredibly straightforward to do. There's lots of data out there. Anyone can go and download the data. the tools like Google Earth and Google Earth Engine allow people to interact with those data sets and do things that were just impossible even 5 years ago. So it's a really exciting time.
Yeah, because I think one of the promises that NASA is trying to make when they, can send data back from one of the rovers, Curiosity or InSight, of course they're going to let the scientists see it first, but they're trying to get it to the public a lot faster than they have before. So that's also really great. Just like you say, the public gets to see that data too. So one last question from Pankaj. He asks, thank you for the wonderful talk. I'm curious how much of your research has been hampered by the lack of good mapping data of when earthquakes have happened and their intensities.
Yeah, I think this kind of links to Claire's question earlier about historical information. So there's particularly when you go back in time and you're trying to understand previous events, the data gets worse and worse. And so some parts of the world have good historical records. Perhaps there were monasteries where people wrote things down, but often it's a real bit of detective work. And again, some of my COMET colleagues, particularly Richard Walker in Oxford, James Jackson in Cambridge, and others, are really skilled at doing some of that detective work and finding out what happened historically, and then using different types of satellite imagery, actually using optical images, very high resolution imagery, to try and look at features in the landscape and how and where they've been eroded since the earthquake. You can see some characteristic patterns. You can then go and dig trenches and collect samples and really try and understand that historical data, even if the earthquake was sometimes thousands of years ago. So it can be done, but it's harder the further back you go. And of course, now we have such a fantastic satellite systems, we're able to get much more detailed information on earthquakes going forwards.
Wonderful. Thank you so much, Professor Wright, for being with us, even though you're not feeling too great today. You really appreciate you being with us.
I coped better this evening than I did at lunchtime. So I think I went slower and spoke quieter. And I think my voice, I also was, I had about 3 cough sweets beforehand, so I survived.
Well, we appreciate that very much. And thank you to all our attendees who are with us this evening. Really great questions. Always impressed by our RAS audience and the questions that they ask. So just thank you again, Professor Wright, for joining us. And we have another bicentenary talk coming in October with Professor Emma Bunce. I wish everyone a really good night and to take care. Thank you so much.